Hi everyone, Siddharth here. In today's session, we are going to talk about the concept of UDF, the concept of multiple categories of UDF like scalar UDF and grouped UDF. So let's get started. The first thing in today's session that we need to look at is a slideshow containing 3 slides. So let's see what the first slide talks about. As we know that Spark works on a distributed architecture, which is a master and slave kind of an architecture. And it is written in the base JVM language. So that means all the JVM languages, which is Scala and Java, they both can work natively in Spark, right? So for example, you have multiple slaves, you have a master, all of them have a JVM there, and then you code in, let's say, Java or Scala, and then your code flows seamlessly between master and slaves. The problem starts when you have a PySpark API on top of your base JVM languages, which is the second slide. Now let's talk a bit in detail about what this slide is about. So the user submits a job, it comes to the master, and here you see it is a PySpark job. So that means you have not used Scala as your language for coding. You have used PySpark API, which is written on top of Scala. Right. So now your PySpark related code is going to get converted into the base JVM language code, right? This conversion can happen seamlessly because your PySpark API is written on top of the JVM language. That is the reason you see a Python block here in the master node, in the main node, that talks to the JVM and converts your code into the JVM language code. And once you have the JVM language code, that can easily be transferred to all the executors. And as you already know, all the executors already have a JVM process running, so they can execute your code with ease. The major trouble starts when you start writing Python functions, which is the next slide. So a Python UDF. What is a UDF? So what happens when you have a PySpark API, you still have functions that you can write using the PySpark API that gets converted to the base JVM language natively. But let's say there is a function that is not available in PySpark. So that means you'll have to do a custom function. You'll have to write a custom function from scratch. So in that case, what you do is, because as a developer, we are a bit more advanced in Python. So we write a function in Python, and then we want to use that function in Spark. So how do we use that function in Spark? We use something called as a UDF. Now what happens, this Python related code that we have, this our JVM cannot understand, right? Our Spark architecture cannot understand. This is pure play Python code, right? Now this pure play Python code is there, let's say in the main node. From there, what happens? The JVM just takes this code, which is there in Python, and transfers this code to the executors without converting it into the base code, right? Because now your code cannot be converted into the base JVM language code. The reason is you have written not in the PySpark API, you have coded your stuff in pure Python language, right? So that is the reason this Python code cannot be converted to a JVM language code. So that means JVM in the master node is going to transfer your code as is without even opening it directly to all the executors. Now, all the executors will see that this is a pure play Python code. This is not a Scala code. This is not a Java code. This is not a PySpark code. So in that case, JVM at the executor says that I don't understand this code. Let me trigger a Python process in executor, and I will pass entire code to this Python process, and Python process will figure it out what to do with the code. So now you see where the complex structure begins. Your entire Spark architecture does not have any know-how of your code. They cannot understand your code. They cannot convert your code to the base language, which is Java or Scala. They cannot do anything with your code. The only thing the Spark architecture is going to do, it will trigger Python processes that will just read and execute your code. So this is the bottleneck. Your code is not understandable by Python. Python cannot do any optimizations on your code. For example, there is an optimization called as adaptive query engine, right? That kind of, we will discuss in a bit detail about adaptive query engine in the later session. But that is an optimization that cannot be applied to this kind of a code because Spark architecture does not understand at all what your code is all about. It just transfers it. So that was about the PPT. Let's go back to the code to see what it is all about. So we have three base categories of UDF. One is a basic UDF, then is a scalar UDF, and a grouped UDF. So let's see what our data looks like. As you have seen in the previous session, my data has three columns. One is a short name. So this is the name of the stock on NASDAQ. So for example, CPB is a stock name. And on 7th of January 2004, the value of the stock or the value of the stock was 216.4 on NASDAQ. I have renamed this columns as sales just for ease of understanding. If somebody wants to think in terms of sales and not in terms of the price of the stock, they can just think that this much sales happen for a stock called as CPB, right? Now let's go down. So in this UDF, this is the basic UDF that we can do. What we are trying to do, we are trying to convert our stock name, which is let's say a capital A, into a small array. Now this is very simple. We don't need a UDF for this. We can directly do that in Spark. For example, you see a command here. There's a lower function in Spark that we can use to convert this into a lower case. But just to explain you the concept, I've written a UDF also. The output of UDF is this column, updated short name UDF. And if you see the UDF, it is just a Python function. The only thing that makes it convert to a UDF is this decorator called as @UDF, and string is the return type of the output. So there is a short name dot lower, that's a string, right? So that's the same thing that is mentioned here. So it is a plain Python function which gets converted to a UDF by just writing this decorator on top. Another important key concept to note is a basic UDF will be executed row by row. That means row number one, short name value A will be picked up, it will get converted to A. Then row number two, short name, again A is picked up, converted to A. It is a row by row computation which is happening in UDF, which is extremely slow and painful. Now let's move to the next category of UDF. Since this row by row operation is pretty painful and creates a performance bottleneck, Spark came up with something called a scalar UDF, which is also called a scalar vectorized UDF, Pandas scalar vectorized UDF. Now, what happens in this kind of a UDF? You see the function, it is exactly same. Instead of lower, I am doing short name dot upper. The only thing that majorly changed is this parameter here. I've just added one parameter on the decorator Pandas UDF, which says Pandas UDF type dot scalar. Now this command, when I executed it, it gave me an error. The error is series has no attribute upper. So let's try to understand what is happening here. You are trying to call this function and pass the value of the column short name as an input to this function. Now what happens? This short name is not passed row by row. Rather than that, the short name column is actually a series object, and that complete series is passed all together at once to this Pandas scalar UDF. And so that means this short name is not a row by row value. It's not a string. Now it is a series object or a Pandas series object. Why I'm talking about Pandas? Because this is a Python function that has Pandas. So basically what your Pandas scalar vectorized UDF is doing, it is converting the input that you are passing to a Python Pandas series object. So that means this short name which is passed here, it is a series object. So what that means is this short name column is a Pandas series that gets passed to the function. And series does not have any function called as dot upper, right? Because it's a Pandas series. You cannot do dot upper in Pandas series. So to overcome this error, the only thing that we changed is we added a .str after the series name, right? That's all, and it got changed. So the difference between the base UDF and the scalar vectorized UDF is that the scalar vectorized UDF, you pass a series object, a Pandas series object. This conversion from a PySpark object to a Pandas series object is taken care by something called as an arrow. This is a framework that is quite popular nowadays. It converts an object from one language to another, from one object to another kind of an object, and it does it quite fast. So that is what your scalar of UDF is based upon. Now let's move ahead to the last variety of UDF, which is group map UDF. This is also based on arrow. So here what we are doing is we are converting a PySpark data frame into a pandas groups data frame. What do you mean by pandas group data frame? So basically when you have a data frame in pandas and you use a group by operation, group by group data is passed to the function. Let me go to the example to make it a bit more detailed. So what I'm doing here, I'm doing a group by operation on short name and I'm applying this function. So short name is having all the stock values, right? So all the stock values, right? A, G, CPG, all these are stock names, right? So what happens internally when you use a group map UDF, all the rows belonging to AAG form a group and are passed to UDF. So that means all the rows in my PySpark dataset which belong to AAG, all of those rows as a group get passed to this pandas grouped map vectorized UDF, right? So it operates on a group. It operates on a group object in pandas, right? Again, the feature that is there for converting a PySpark object into a pandas group object is arrow. So arrow is the framework that does this conversion. Now, the function is very simple. The function just does a cumulative sum. It can be done in Python, it can be done in Spark. I have just written a UDF to do it because I just wanted to explain you the concept. But normally we don't use UDF if the same thing is available in Spark. We only use UDF if the function is not at all available in Spark. Right? So I use cumulative sum in UDF because I just wanted to explain you the concept with these. Now let's see the output. As you can see the output, I was trying to do a cumulative sum, right? So my short name and the order by is based on date and the cumulative sum is on sales. So this is the last column is the cumulative sum column. So that brings us to an end of the third category. Another important concept to understand is how to test your UDF. One more thing that you might have noted here is I have a print command inside the UDF. Now we are working in a Spark architecture, but UDF is pure Python. So that is the reason you don't see that in logs here. Otherwise you would see a print command getting printed here. The way to look at the Python logs, you have to go to Spark UI and open the logs, which is a bit more hectic. So how to make it a bit easy for you to test UDF? You convert your data frame into a group object in Python pandas. So what's happening in this? So let's say I'm filtering by A. So that is the stock name. So all the rows with stock name as A make a group in pandas. This is what it is doing. You're making a group, you're making a data frame of all the rows which have stock name as A. So you made a group in this line, and now that group is getting passed to this function group map UDF. Now here, whatever print statements that I typed above will be seen. The reason is you have converted your PySpark object into a pandas object, and pandas object do not operate natively in a distributed environment. So your function now is operating on the driver node only and not on the executors. And whatever is executed on the driver node, you can see that print statement easily, right? So this is the way you can test a UDF on driver node. Now let's see another example. There's nothing much here. It's very simple. I'm just trying to show you that whatever I did in UDF or a pandas grouped map UDF, which was running sales or cumulative sum, the same thing I could have done natively in Spark. That is what I'm trying to show here. If you see here, I already have a window defined before. So it's a window function, cumulative sum, running sum. We have already discussed it in previous videos. In one of the previous videos, which talks about aggregations in Spark, I've already covered the topic of window aggregations. So Python or PySpark has a window aggregation with which you can do cumulative sum natively in Spark. We don't need to use a UDF. So this brings us to the end of this session. Thank you all. Have a great day ahead.